All right, let's just jump right in. We're about to peel back a layer of the reality you know and take a look at the hidden architecture of the universe itself. We're going to explore the story of the so-called God particle, not as just some buzzword, but as the invisible quantum hum that is literally stopping our world from flying apart.
I want you to start with a really simple question. What makes you solid? No, really, look at your hand. You see it? You feel it? It seems pretty substantial. But have you ever stopped to wonder why? What is it that's giving your body, and everything around you for that matter, its substance?
Because here's the crazy part. According to our best understanding of physics, you shouldn't be solid at all. Seriously. Without one very specific field that fills the entire universe, the basic particles that make you wouldn't have any mass. You, me, this planet, all of it would just instantly dissolve into pure energy, zipping away at the speed of light.
So, what is this mysterious force that's holding us all together? Well, the answer lies in something physicists call the Higgs field. I want you to think of it as the universe's invisible ocean. It's this fundamental energy that's everywhere, touching everything. It is literally the architect of our physical reality.
And this is what makes the Higgs field so weird and so different from anything else. You know, a magnetic field needs a magnet, right? A gravitational field needs a massive object, like a planet. But the Higgs field, it's just on. It's on everywhere, all the time. It has a constant value, even in the most perfect, empty vacuum of deep space. It's like the background hum of the entire cosmos. Which, of course, brings us to that famous nickname. And no, it's not a religious thing at all. The story goes that Nobel laureate Leon Lederman, after decades of frustratingly searching for it, wanted to call it the goddamn particle. You can imagine why. His publisher thought that was maybe a bit much, so they changed it to the God particle, and, well, the name just stuck. Most physicists kind of roll their eyes at it, but you have to admit, it does capture just how fundamental this thing really is. Okay, so this is a super important point. We have to separate the field from the particle. They are not the same thing. The field is that calm, ever-present ocean. The particle, the Higgs boson, is what we actually detect in our experiments. It's like a splash, a little ripple, a tiny localized flicker of energy in that field. We can't see the whole ocean directly, but we can absolutely prove it's there by making a splash and watching for that ripple. So how does this invisible ocean actually give stuff mass? It all comes down to an idea that feels a lot like a kind of cosmic drag.
The best analogy is this. Imagine the Higgs field is a crowded cocktail party with people spread evenly throughout the room. Now, a massless particle, like a photon of light, is like a waiter who can zip right through the room without anyone stopping them. No interaction means no mass. An electron, though, is like a minor celebrity. A few people might stop to talk, creating a little bit of drag, slowing it down. That's a little bit of mass. But then a superstar walks in, like a top cork. They are instantly mobbed. It's incredibly difficult for them to move through that crowd. That intense resistance, that drag, that is what we perceive as mass.
You see, this is a total game changer in how we think about the universe. Mass isn't some property a particle just has, like its electrical charge. Mass is the result of a relationship, an interaction. It's not something a particle possesses, it's something that happens to it as it tries to move through the Higgs field.
But you have to remember, for decades, this was all just an incredibly beautiful theory. To prove it was real, scientists had to embark on one of the greatest quests in modern science. They had to go hunt for that tiny ripple in the cosmic ocean.
And what a journey it was. I mean, the idea was first put forward way back in 1964 to fix this giant hole in what's called the standard model of particle physics. It then took almost 50 years, and building the Large Hadron Collider, the biggest, most complex machine ever built by humanity, to finally get the proof. And then, on July 4, 2012, the world of physics changed forever.
They found it, a brand new particle with a mass of about 125 giga-electron volts, or GeV. Now, that's just a unit of energy that physicists use. But that number wasn't just any number. It was the specific signature, the exact size of the splash they had been hunting for all those years. The ripple was real. And they were sure. In particle physics, the absolute gold standard for a discovery is something called 5 sigma. All that means is there was only a 1 in 3.5 million chance that the signal they saw was some random fluke. It was real. The standard model of particle physics was finally complete. But, as it always is in science, completing a map doesn't end the exploration. It just shows you how much more territory there is left to discover.
Because here's the twist. Finding that final piece of the puzzle didn't end the story. Oh no.
In fact, it blew the doors wide open to even bigger and frankly much stranger questions about how the universe really works.
So, with the standard model complete, you might think, great, physics is done. Is the book closed? Not even close. The discovery of the Higgs wasn't the epilogue to the story. It turns out it was the prologue to a much, much stranger one.
You see, the Higgs itself poses some huge new mysteries. For example, our theories predict that the Higgs particle should be trillions of times heavier than it actually is. It's unnaturally light. Why? And even more profound, the Higgs might be our only direct line of communication to what's called the dark sector, the invisible dark matter that makes up 85% of all the stuff in the universe. Suddenly, the Higgs isn't just a source of mass anymore. It might just be a portal to an entirely new, hidden reality.
And this brings us to what might be the most profound implication of all. The very existence of the Higgs field, at the specific strength it has, suggests we live in what you could call a Goldilocks universe. It's not too hot, not too cold, it's just right for us to even be here.
Our entire existence is balanced on a razor's edge. I mean, look at this. If the Higgs field were just a tiny bit stronger, atoms would collapse on themselves. If it were a tiny bit weaker, atoms couldn't form stable bonds. That means no chemistry, no water, no stars, no us. The value of this field seems exquisitely, almost impossibly fine-tuned for life to exist.
In fact, its particular mass points to something that is truly mind-bending, that our universe might be in what's called a false vacuum. Think of it like a ball resting on a high ledge instead of in the deepest part of a valley. It's stable for now, but it's not perfectly stable. If something with enough energy ever came along and knocked it over, a bubble of true vacuum would expand at the speed of light, rewriting the laws of physics as it went. The universe wouldn't explode, it would just be, well, deleted. But hey, don't worry, the chances of this happening are pretty much zero for billions upon billions of years.
So, we're left with this enormous question. Is our finely tuned universe just a wild statistical fluke in some infinite multiverse? Or is this precise tuning a hint, a signature of some deeper, underlying order that we haven't even begun to understand? The discovery of the Higgs didn't just give things mass, it fundamentally reshaped our view of what it means to exist, showing us we aren't just a collection of objects in empty space, but that we are all just ripples in one unified cosmic ocean.